finish off this set of videos with a couple of random examples here. First example, we have this situation. You can read it as I draw the picture. So the picture here is that we have a spy, okay, at this box, is watching a rocket is being launched upwards. And so the question here is, he's watching like this, and we're trying to relate together this angle theta that he sees with the height of the rocket and time. So what's going on? Let's read this through. So the rocket is being launched vertically upwards. The distance that the rocket is, the launch pad starts 6 kilometers away. The rocket is going up. The angle here between the telescope and the ground, the line of the telescope and the line of the ground, is pi over 3. The angle is changing at a rate of 0.9 radians per minute. So the question is, at that point in time, what is the rocket's velocity? So, okay, what is our list of things going on here? Identify variables and the rates that are related. So let's talk about that. So let's suppose that y is the height of the rocket. So really, what is the rocket's velocity? We're being asked for dy dt here. And we're also being told that, well, we have this theta here. We're told that d theta dt is 0.9 radians per minute. So what's our goal? Dy dt when theta is pi over 3. Okay, so at this point then, the most important thing is always to find the equation that relates everything together. So what do we have here? So we have theta, we have y, and we have 6. And so what relationship do we have? Think of a little bit of trig. Y over 6 is the tangent of this angle theta. So we can write that down. That tangent theta is y over 6. And now we differentiate both sides of this with respect to t, as usual. And so what do we end up with? So on the right, that's just going to be 1/6 times dy dt. Pretty straightforward. On the left, the derivative of tangent is secant squared theta. But as usual, we have to apply the chain rule here to multiply by d theta dt. And so this is our equation that relates the variables, and we differentiate so that we have everything, a relationship, not just between the variables, but between the rates themselves. Okay, so now we have to plop in all of the information that we have. So what do we have? D theta dt is 0.9. So 0.9, and we're interested when theta is pi over 3. So this is secant squared of pi over 3 times 0.9 is equal to 1/6 dy dt. So solving this for dy dt, so we have 6 times 0.9. Secant, remember secant is 1 over cosine. I think it will be a little bit easier to express as 1 over cosine squared of pi over 3. And so the only thing that we have left to do is, well, what is cosine of pi over 3? Cosine of pi over 3 is, of course, going to be 1/2. And so here is your dy dt. If we want to crunch all of that out, it is 21.6 kilometers per minute. So So you can see that this is useful. If you're the spy and you're trying to figure out how fast is this rocket going up, if you know how far away you are, and you can tell from your observation how fast theta is increasing, you can tell how fast the rocket's going up. I think that seems like a pretty useful application of this kind of related rates. You have a little bit of information, and you can use this kind of analysis here to figure out the information you really care about. Okay, one last problem to do. Here is a electricity circuits kind of problem. So if two resistors with resistances R1 and R2 are connected in parallel, then the total, the overall resistance, is given by 1 over R is 1 over R1 plus 1 over R2. So let me just say, if you've, this very well could look familiar if you studied this previously. If you haven't studied this previously, don't freak out. This is, we're giving you the information here. The only information you would really need to do this is this equation right here of how R, R1, and R2 are related together. So the overall the overall resistance is related to the these two resistances of the resistors in this fashion. So we are told that R1 is increasing at a rate of 0.6 ohms per second. Ohm is the, if you're unfamiliar with this, ohm is the unit of resistance. R2 is increasing at a rate of 0.4 ohms per second. So how fast is the overall resistance changing when R1 is equal to 160 and R2 is equal to 200 ohms? So this one, we've basically, so in our list of things, we basically already have the variables and the rates that are related. R1, R2 is what's going on here. We already have the equation that's relating the variables. So what's left for us to do here is to differentiate our equation with respect to time and then plop in things. So let's do that. And so what do we end up with? So the derivative of 1 over r, that's just going to be, so minus 1 over r squared times dr dt. All of these we're basically using the fact that like 1 over r is equal to r to the minus 1, and we're just using the power law at this point. Okay, 1 over r1, that derivative is minus 1 over r1 squared times dr1 dt. And the derivative of 1 over r2 is minus 1 over r2 squared times dr2 dt. So this is how we went from how the resistances are related to how the rates of change of the resistances are related together. So at this point we see there are r dr dt, r1 dr dt, dr1 dt, r2 dr2 dt. So there's 1, 2, 3, 4, 5, 6 things in here. The thing we're looking for, how fast is r changing? So dr dt, that's what we're looking for. And so we're going to try to plop in values for r, r1, dr1 dt, r2, dr2 dt. So 4 of the pieces of information are given to us right in here. R1 and R2 are changing at 0.6 and 0.4 ohms per second. And R1 and R2, we're told, are 160 and 200 respectively. So minus 1 over 160 squared minus 1 over 200 squared. So now the only thing that we have left is that we have to fill in what is R itself. Now we weren't told what R is, down here, we have to use this equation that relates r to r1 and r2. We have to plop in the values of r1 and r2 up into this equation so we can figure out what r is. So let's do that. 1 over r is 1 over 160 plus 1 over 200. If we combine this together, we can combine this together as 9 over 800. So 1 over r is 9 over 800. So r is 800 over 9. And so this ends up being, let me find which marker do I want? This one? Yeah, I want this one. So minus 1 over 800 over 9 squared times dr dt is equal to this. So we rearrange, we move this to the other side, and so we end up with dr dt is minus 800 over 9 squared times minus 0.6 over 160 squared minus 0.4 over 200 squared. And crunch, 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 it ends up as 107 over 405. Or that looks like about 0.26 to me. And what are our units? Ohms per second. So that is one last example here of, what makes this one different. We had 3 different variables that were all related here. So, but other than that, everything crunches out in the same way. I guess the other interesting thing was we had to use our equation carefully, figure out what was r at the point that we care about. That wasn't explicitly given to us in the problem. Okay, so that wraps up our set of videos on section 3.10, and I guess that wraps up our set of videos on chapter 3.